So let's get started. For now, things are working. So let's see when it breaks. Any questions about homework 1, first of all, before we get into the today's lecture? So we had lots of discussions on campus-wide about, I think, immediates and labels and those kind of things. Is there anything that you want to ask and still unresolved, or you think you're good? Okay. Yeah, I think so. Part of the learning is also you kind of try different things and see the details. So part of it, we intentionally didn't really go into the examples and details because we wanted for you to also try and see the differences. But if you're still in doubt about anything, feel free to reach out to me or the TAs. Okay. Cool. All right. So last time we kind of like stopped here. We talked about a bunch of different instructions, and we said that there's generally this this table that the assembler use in order to create the machine code. To make things simpler and kind of like more structured and more systematic, RISC-V using this specific groups of instruction types, which are 6 different instruction types that we usually use. R typos are the most common ones, which is all these different ALU operations. The I type one is similar to R type, but it just use the immediates. The S types is usually for store. The B types is for branches, and U and J types are also used for branches and some other instructions that we didn't really get into. And if you look at this left side, you will see that these all instructions kind of like goes into one of these categories depending on how they use different areas. And one big thing is that we try to make it as simple as possible to make the decoding simpler. So we usually, for example, make sure that all of them have the same place for the opcode, all of them have the same place for the sign bit, and all those things. So all of them has the same place for the RS1, for example. So it's kind of like we try to make it as structured as possible. But on the other hand, since we have different types of instruction, then we need to play with some of these different categories. So for example, immediate is the one that is kind of like, moved around and scattered around in these different instructions. So you see some of them, for example, has the immediate, some of it here and some of it there. There is those that are like, very complicated and use it this way. So there, and then there's one that is kind of like do all these weird stuff like that. So it's just generally there are 2 reasons we are doing this. One is to make sure that all the other instructions kind of like follow the same format, and the second thing is that for making sure that, for example, the sign bit is at the right place for all the different instructions. So these are the reasons that we do these kind of things. Okay. So the rest is just, I leave it to you guys to go through it. Part of the homework was actually intentionally letting you to explore this and figuring out different parts. In this lecture and next lecture, we will talk about the microarchitecture, which is basically telling you about how we are building the hardware base of this table and this instructions. And there we're gonna also talk a little bit more about the differences about these different parts, because when we are building the hardware, we need to decode these, so we need to know this better. And in the project, you will also implement this in a C++ language, and there you also will see a little bit more detail about these. Any questions? Yeah.
The immediate, it's like 11 is outside of the spectrum for 12 and the 5.
Oh, like why they put the 11 on the right side? So they really wanted to put the sign bit on the left side, and I think the reason is it's probably using the lowest 3. So they wanted to use the lowest 3. So the 11 is the most significant bit, right? So they want to use that for decision purposes of where it has to jump. And then also they didn't want to move the sign bit with it because they want to leave the sign bit on the left side. So the 11 bits is used for kind of like, for making the addition easier. And then the sign bit is left at the same place that it was before. Once we kind of like show you the microarchitecture for doing the branching, it makes a little bit more sense. But also some of it is just decisions that they made. It's not something that I say, oh, it would be wrong if I put 11 on the left side with 12. It just makes the hardware more complex. Any other questions? Yeah. Oh, by the way, the question was why the 11th bit is on the right side and not on next to the 12th bit. Yeah, sorry I forgot to repeat. Yeah. So the question is why some of the immediates have 13 bits and some of them don't, right? Is that the question? Okay. So the amount of the number of bits that we can use for immediates is really constrained by the other things in that instruction. So for example, those that require an opcode RS1 and RS2, and then some of these things that we call find3, which is basically kind of like telling what is the difference, different types of branches and so on. So this means that we are only left with this area here, this area here, and this area here for our immediates. So that's kind of like our constraint. For other cases, like for example the GL, you see that we have plenty of space here, and so we can have a much bigger immediate. So how many bits are we using for immediates? Really a function of how many other spaces we need to capture and allocate for the other activities in that specific instruction, and then whatever remains goes to the immediate. And if by any chance you need bigger immediates, then it means that you have multiple instructions to do what you want to do. And for example, for branches, what you can do is jumping maybe twice, or using like PC relative or register relatives jumping and things like that. But again, remember that we are doing RISC, which means that everything has to stay at 32. So for example, one of the goodness of CISC is things can be, variable size. So for example, if you want to have always 32-bit immediate, you can. For some instruction, that means that you have an instruction that has 32 bits. In some others, you might have an additional, for example, 16 bits added to that. You have 48 bits and so on and so forth. But the downside of this is that the decoding is much more complex, because here we know that everything is 32 bits. So we just get the whole chunk and then do the decoding and all those things. Versus for CISC, we have to first read the first 32 and then decide whether we need to fetch more or less and so on. So it's kind of like a trade-off between these two. The SHAMP I'm going to get to actually. The question is, what is that this one here? So this one is only for shift instruction and decides how many bits are we shifting to the left or right, and whether it's a logical or whether it's an arithmetic. Oh, we're going to get to that later once we talk about SLI. Yeah. So the question is for branch instruction for immediate, where is the 0th bit? If you remember, for the branch, we just ignore the first bit and we start from the second bit. The reason is we're assuming that we only jump to the even memory addresses, just because to make the two things. One is to make the hardware simpler, and the second thing is that this additional bits means that we can jump higher, right? So we can jump to further addresses if need be. Okay. So far we talked about building an ISA. We said that basically the first thing is using a compiler to transition from the high-level language to assembly. How do we do that is actually a separate course, which is a compiler course. Then we need to find a way to generate the machine code, which basically what we discussed majority of last week, last lecture, and the table that I show you now. Then now let's actually look at these other two things. So now we have the machine code, then what? What should we do? And then after that is, okay, now we are looking at the hardware side. We have the machine codes, we have the list of instructions. then what should we do, right? How the hardware understands this and how the hardware runs this. That's the main question that we want to answer today. So I told you about how we, run things and think about instructions and machine code in hardware. We said that we are using store program computers. To give you a little bit more background, we said that, we assume that the program is nothing different than the data that we have. So we basically, if you think about our memory as this lines byte by byte, some location in this memory is for instructions, and some of these would be for example, data. And there is, in terms of storing things, there is no difference between what is instruction and what is data. And it's the operating system's job to kind of like structure memory in a systematic way to make sure that things are in right locations. And it just tells the processor using this register called the PC or program counter that where is the beginning of this block of instructions, right? That's all the processor needs to know. And after that, the programming model that we are assuming, the execution model that we are assuming is that the processor will read these instructions one by one, execute them, do whatever it needs to be done with that instruction, which we're going to talk about in this lecture, and then go to the next instruction and next instruction and next instruction until we finish all the instructions for that program. And then it will notify the operating system that I'm reaching to the end, and the operating system will take over, and then the story continues. Okay, so that's kind of like the programming model or execution model that we use in all these computers, and this is typically called as a store program model. There are different types of other types of system and execution model, such as data only, which sometime in the future we might actually reach into, especially at week 10 if you have time. I'll talk about it a little bit later. This store program is named after this person who was kind of like one of the early researchers in this domain. So we usually call this a von Neumann machine or von Neumann model. Okay. So to give you again a cartoonish picture of what's going on, we have our program here. We use the ISA in order to create the assembly. So keep in mind that our program could be in any language, but once we translate it into the assembly, we have to assume what ISA, the specific hardware that we have supports, right? So here is like could be x86, could be ARM, could be RISC-V, and so on. Then we have our assembly code, which we extensively talked about. Then we use that table and we use the assembler in order to create the machine code. So this machine code here is basically, list of zeros and ones, right? And then we put this into our memory. Part of the memory would be filled with this machine code. And then we're going to say that, oh, this PC, which is a specific register inside our CPU, will be pointing to the beginning of this instruction blocks. Okay, so this is kind of like again the repeat of what I just said in the previous slide, with some pictures. Okay, is that clear, everybody? Anybody has any questions about this? Yeah. So the question is that is PC one of those X registers we talked about, or is it a separate register? And the answer is it's separate. So we still have our 32 registers. One of them is hardwired to 0, which is X0, and then the rest can be used for any other purposes that we want. And then the PC is a separate register; it doesn't count toward that. So the question is, does the assembler count as part of the ISA? And can you elaborate more? What do you mean by count? So the question is that if, for example, we use a specific ISA, does the assembler come with the compiler or not? So we usually refer this to as tool chain. So we usually say, for example, I use RISC-V tool chain. And when I say tool chain, I mean the compiler, the assembler, and there are other steps that we didn't go to, like linker and all those things, that are also all part of what's called a tool chain. And usually when you use an ISA, you develop the whole tool chain, but each of them are, you can think about it as a separate program. So you can, for example, change your compiler, but keep your assembler, or change your linker, keep your assembler, and all those things. But collectively, we refer them as two tool chains. Okay. So this second part is also, we kind of now getting it. We uploaded using this graphic that I'm showing here. So now actually let's go to the more complex question, that how does hardware actually understand this? And generally, how do we implement an ISA in hardware? Okay. And the answer to that is, we call the hardware implementation of the ISA microarchitecture. Okay, so the microarchitecture is that we are given an ISA with all these, different units and blocks, RS1, RS2, and all those things, and we need to implement it in literal hardware blocks, and that's what we call a microarchitecture. One thing to note, that given that, for example, we have the same ISA, doesn't mean that the microarchitecture are exactly the same thing. So for example, as I told you, Intel is always using AMD 64 as their ISA, but for every generation, they are making changes in their hardware. So their microarchitecture is changing from one generation to another generation. Same story for ARM, and same story for all these other companies. So the microarchitecture could be different for a given ISA. Okay, so it doesn't mean that we always have to make one thing regardless. And once I describe to you what the microarchitecture is, you will see that these are the design decisions that we make, and that's why there are different microarchitectures. And to give you kind of like, a big picture of, like, give you an idea of what we are looking for in terms of developing and designing this hardware. As I said at the beginning, the number one goal is making efficient computers. And as I said, by efficient, we usually mean a system that has the highest performance. So we really want to achieve and build a hardware that can execute this instruction as fast as possible. Okay, so that's the goal in microarchitecture. What we're going to discuss this lecture and next lecture, we want to eventually reach to this complex system. You see there are multiple different components, such as, you see the PC here, you see things like register file here, you see all these different things, and there are, like, different, connection between one unit to another unit. There are these blue lines, which is coming from the controller and all those things. And in this lecture, we will talk about all these individual units and how we are connecting them in order to create this big microarchitecture, which is the hardware implementation of that ISA. Okay, and this will be something that you will also implement in your project number one. So basically, all these different components, think about them as different functions, and these wires are basically the inputs and outputs of those functions, and that's what we will implement in our project as well. Okay, so now let's go and get into it. So in order to understand what we need to do, what are the steps, we need to first understand the life cycle or step-by-step execution model of an instruction. Okay, the first thing an instruction needs to go through is the instruction needs to be read from the memory. Remember, we said that basically the CPU use this register PC to go through the instruction to the memory and read things from it, read the instruction from it. This is basically what we call as fetching instructions or reading instructions. The first thing for every instruction is that we have to go to the memory and bring that 32-bit value to our CPU. Okay, so that's the first thing we need to do. And for now, let's assume that when we are referring to instruction, we call it instruction memory. And when we are referring to data, we call it data memory. In reality, they are the same thing, but for now, to make things simpler and to represent things simpler, think about the instruction and data. They are stored in two parts, different physical parts of the memory. Okay, so the first thing is fetching it. Once we fetch the instruction, then there are steps in order to understand what are the operands, if we need to go and read the operands, and then do something with it. So the second step is we need to read the operands or load the operands. And if you remember last time, we said that we are three different options or three different types of operands. We have immediates, we have registers, and we have memory operands, right? And this memory is basically data, right? It's not instruction anymore. We need to read operands from some lines of memory and bring it to our system. So for example, for reading the registers, we need the register number. Remember, we had like X1, X2, X3. So we need to know which register we need to read, right? Or we need the address of the memory line that we need to read, right? That's the second thing we need to know. Then once we have our operands and we have the command that we want to execute, then we have to execute this, right? And what does execution means? Remember, I told you that we have three different command types. We have arithmetic, we have control flow instructions, and we have memory type instructions, okay? So depending on what that instruction is, we need to do some action. If, for example, it's an R type or ALU operation, we need to, for example, add them together or subtract them together. So there is an arithmetic operation that needs to be handled. If it's a control flow operation, we need to first, for example, compare to see, for example, whether RS1 is equal to RS2. If that's the case, we need to jump. If not, we have to just ignore and continue and all those things. So by execution, we mean this type of operation. Depending on what the command is, we need to make some decision. We need to actually run some executions. And then once we do these, we need to store this information back into either the register file or into the memory, because whatever instruction we do, we have to store it somewhere and then move on to the next instruction, right? If we just ignore that operation that we did, there's no place to record this. So we always, everything we do, there's a storing process needs to be done before moving on to the next instruction, okay? So the results should be stored somewhere, either into a register file if you have an RD, or into some memory if there is like a store instruction, okay? So the results needs to be stored somewhere. And finally, we need to update our PC to go to the next instruction. As I said, the default is always we go to the PC +4, right? If it's not a control flow instruction, but if it is a control flow instruction, then we need to find the right place for the PC to jump to, right? This could be a JAL or JALR instruction. It could be a branch instruction. So we need to figure out whether we need to update the PC with PC +4 or whether we need to update the PC with the destination PC that we need to. Question? So the question is that the second step that says operands should be loaded, where are we loading them? We are loading them temporarily into our wires. So think about when we are saying loading, means that one function needs to pass the inputs to another function. So we physically like wire them together this way. But all these steps that I'm showing here, I'll actually show you the pictures and the actual hardware for it. Okay, so the last step is that the PC should be updated, and once the PC is updated, then we are basically going back to step one, the start of the new instruction. We have to fetch it first, we have to load the operands, we have to execute it, we have to store it, and we have to update the PC again and go to the next one, the next one. So this basically becomes a loop which starts from the very first instruction of our program and continues all the way to the end once the program is finishes. Once that process is done, then we usually use what's called a system call, which is jumping to another function, which is this function inside the operating system. So we give the control back to the operating system, and the operating system will continue executing things, okay? So this is basically kind of like, think about it as a one worker, which is a process, do something, and once it's done, come back with the results, tell the boss or the operating system that I'm done, just go and do whatever else that you need to do, okay? So this is kind of what we call as the life cycle of instruction, and this is what we need to implement in hardware, step by step. And this complex picture is nothing but just adding these things together and assembling them together in order to create this piece of hardware. Okay. So let's start this process one by one. The first thing, as I said, is fetching instructions. And as I said, the word fetch is commonly used, and you can interchange it with reading from the instructions. Okay, so the instruction, as I said, this part is where the instructions are stored. So the memory is where the instructions are stored. And in order to distinguish between data and instructions, we call it instruction memory. But as I said before, this is nothing but specific block of one memory that we have. Okay, and the memory has two main things. It needs an address, and it needs to provide the data. Okay, we usually show it this way. So this is basically the input, and this is the output. So what it does is that it says, tell me which instruction or which address you need to read from, and I'll give you that 32-bit value that you want. Okay, so this value here is 32 bits, and this is usually the notation that we show. So if we show one wire, it means it's 1 bit. But if we have this additional line and number on top of it, it just says how many bits this is. So for example, if I do this, it means that this line has 4 bits. And if I do it this way, it means that this line has 32 bits. So instead of like drawing 32 lines, which is dirty and not manageable, we just show it this way. Okay, so the output of this instruction memory, this block, is a 32-bit value, which is the instruction. And the input for that is coming from where? It's coming from our PC. And this is a register, the register PC, which basically says whatever this value, this output for this register, this PC is, it has to go directly to the read address of this instruction memory, and that would be the address to read that instruction. Okay, so remember we said that PC is basically keeping track of next instruction and next instruction. So this is our register. We usually add this tiny rectangle at the bottom to say that this is a register. It's using clock. And I'm going to get to how we build registers very soon. But basically, what this says is that this PC is a physical entity in our hardware. It's a physical register, and it's connected directly to our instruction memory and gives us the address. And the instruction reads this address and provide this instruction to the rest of our hardware, which I'm going to add. So this is the leftmost part of instruction. This is basically step 1 of reading the instructions. So now you might ask that what is this process of reading, and what is a register, and what is the memory, and all those things. These are the things that you probably extensively seen and talked about in your M116/M51 course, but very quickly, I'm just going to briefly go over them. But again, today would be a good time to go back and take a quick look at, like, for example, flip-flops and all those things. We don't need to understand the details of it. We just need to know how they work, because we're going to use them in building our data path. Okay, so we're going to talk about combinational elements and sequential elements, and tell you a little bit about each of them. So sequential logic is something that usually store something inside the hardware. Generally, if you have logic, there is no way that you can store things. So temporary, right? So if you change this value will be changed as well. Versus the sequential logic is basically telling you that you can store things unless you have change in the clock. So we usually typically have either what's called an edge triggered or level triggered clock. In this specific data path that we will talk about, we are only talking about edge trigger sequential logic. What it means is that the inputs to this, what's called a register, is basically the data and the clock. And for now, think about data as just 1-bit value, and clock also as 1-bit value. And what happens is, if there is an edge, for example, in this specific case, we are talking about the positive edge, which means that we are transitioning from 0 to 1. If there is an edge, then what Q will be taking, will be remembering, or will be snapshotting is whatever value that there is in D. Okay, so for example, it's this D value is equal to 1. After some delay, this Q will be equal to 1. Okay, And the interesting thing is that if later on D changes, for example, from 1 to 0, this Q doesn't change, right? The Q only changes when we actually have a pulsing clock, right? And this is basically kind of like think about it as an enable logic for this register. If there is a positive edge, if it's a 0 to 1 transition, then the Q will be updated based on whatever value D has. Okay, and think about it. For example, for our PC, this is exactly what we want, right? PC is our register. It has 32 bits. And it generally doesn't change the PC, doesn't change its value. It always stays the same. Only when we finish the instruction and we want to move on to the next instruction, that's when we want to update this value of PC. So we're gonna issue a clock, and then gonna issue a new value for PC, for example, either PC plus 4 or the target. And this Q, which is the output of this PC register, will be updated based on that after some delays. Okay, so this is basically a sequential logic or a register. An additional thing that you might have in this register is what's called a write enable, which basically says that, you know what, you can also have a positive edge, but if the write enable is 0, we still don't, catch the value. We still don't update the value. So it's basically just giving you additional control for what can be written in this register. And later on, you will see that why we need such a thing in our systems, because there are instructions, for example, that reads from the memory, and there are instructions that writes into the memory. And we only want to update the memory when that write enable is equal to 1. Okay, so the only difference with this picture and the previous picture is that both of them are still edge trigger. When the positive edge comes, they can update their value, the output value Q. The difference is this one, if this write is equal to 0, then the Q won't be updated. Okay, if the write is equal to 1 and the positive edge comes, then the value will get updated. So look at this part here versus this part here. You see that this part here, the positive edge is coming, but the write enable is equal to 0, and you see no change into our Q, although the D has changed, but Q doesn't change. Okay? Any questions so far?
I'm just having a little bit of trouble understanding the D like in the diagram, right? When it like goes inward, I'm trying to understand how that maps back to clock. Right? Like I understand like when clock is 1 or turned on, you have to tell you where it is, if it's clock and writer 1, but that's the only way. How does that? Can you explain again how that relates back to like the diagram?
So this graphic here, right? So the question is, what is this graphic means for D and Q? So what this graphic means is that we're assuming that D or Q might be multiple bits. It's not just one wire. It might be a combination of wires. So that's why we are showing it in this kind of like, a group of colors. And this thing here means that the data has changed. So it has, switched from 0 to 1 or 1 to 0. We don't know. Or it could be multiple bits. So like 4 bits. So for example, it could be 1101 and then change to 1010, something like that. It means that the data has changed here. And if it's just going straight, it means that the data hasn't changed. It's basically just a notation to show you that when the Q gets updated. It's just, you can see that this is not transparent, right? So it's not like whenever I change D, the Q, quickly change. And the change in Q depends on clock and write enable in this case. And if you go back, the value of Q, it only depends on the clock. So you only see the change in Q only after that there is a positive edge of the clock. And you see that there is a slight delay. So it's not like, exactly after this, because these are logic. So there is what's called a propagation delay, because there are delays for gates. So if you switch a transistor, it's not like as I make this transition to 1, this line and this line gets connected immediately. It takes some time. We're talking about nanoseconds and picoseconds, but it takes some time. And if you remember, in the first lecture, I told you that when we are moving from one generation to another generation, transistors gets faster. This is what the faster means here. So basically, this delay gets smaller and smaller when we are moving to a higher trend, to a lower technologies. Any other questions? Okay, so we know now what's an edge trigger register is, and we also know what is an edge trigger with write enable is. Okay. So now what is a memory? Think about memory as an array of these registers. And we usually structure a memory into a 2D array that we usually call this way the width and this way the length, or W and L. All this widths together becomes a memory line. So for example, I told you that our memory is byte addressable, which means that this is basically each of these is 1 bit. 8 of this together creates 1 line. Okay, so 8 bits creates 1 line. So 8 of those registers needs to stay together to create 1 line for us. And then we can have multiple lines in the memory, right? The lines and widths has nothing to do with each other. You always have 8 bits or 1 byte of memory line, but you can have thousands or 10,000s or millions of lines in your memory. That's your L. Okay. So the question is, okay, so now we are saying that, for example, the instruction memory, basically what it does is that it gives you an address. Whoops. It gives you an address and goes into this memory, and magically there will be a data outside, right? It's the instruction, basically. So how does that work in terms of the circuit? So usually think about, like, very simple scenario. We have only 2 lines. Of course, we have millions of these lines, but think about it as 2 lines. So the address is just 1 bit, and it's either 0 or either 1. And then we obviously have 2 lines. In this case, let's think that each line is only 4 bit. I'm just simplifying the example. So in order to pick between these two, what we need is a multiplexer. Okay. So what we need to do is basically we are saying that, you know what, let's say all of these are actually putting their outputs into this multiplexer, and this address is basically the selector of that multiplexer. For those of you who don't remember what the multiplexer is, multiplexer was logically this thing that has a selector, and usually it only has 2 inputs. The selector basically says which of these 2 inputs we have to select. Okay, so if the selector is 0, it means that we have to select this. If the input is 1, we have to select this. Okay, so this is basically what we're showing here. How do we implement a multiplexer? You can go and check out your M51 course. But basically, our address acts as the selector in this case. For 2 lines, our selector is only 1 bit. For million lines is log 2 of that number of bits, right? So this mux is basically telling which one are we picking. Okay. And basically this output is the output of this, the output of this, the output of this, and the output of this all together. So I'm not showing 4 lines. I'm just showing 1 line to make it simpler to show. All right. Does that make sense? Any questions here? So this is just a simplified version of how we are reading things from memory, and how does the impact of the address, like how does the address actually selecting all of these different lines in our memory. Another question is, when we are saying memory, are we talking about just the exact same implementation of registers, just 8 of them together to make the memory? And the answer to that is no, we cannot use the same structure that we use for registers for memory. And the reason is that building memory requires different transistors, and we usually have 4 or 5 different options in order to create our memory. The first one is what we call registers. So you can call it, flip-flops, or in some cases latches. The good thing about registers, they are very, very fast, and you can read them together at the same time. So you can access multiple registers at the same time. But they are very expensive. And by expensive, I mean number of transistors that needed to build 1 bit of registers is usually in order of tens. With all the circuitry around it, we need tens of transistors to just store 1 bit. Okay, so we cannot really afford to have megabytes, for example, of registers, because we are talking then about millions and millions of transistors, and we have power issues, we have area issues, and all those things that we discussed in the class so far. Okay, so what are the other alternatives? The other alternatives is what's called an SRAM, or a static RAM, random access memory, or a dynamic RAM, or DRAM. The difference between the two is kind of like they are another tier of memory. The SRAM is relatively fast, but it's slower than registers, but it's faster than DRAMs. You can read one word at a time. You can read 32-bit at a time, the way that we designed them. And they're still relatively expensive. We usually need 6 transistors, a little bit more, to build 1 bit of SRAM. Then we can move to DRAM, and DRAM only requires 1 transistor, typically. But they are much, much slower than SRAMs and the registers, okay? But on the other hand, they are very, very fast. They are very, very efficient in terms of area. Another problem with DRAM is that unlike SRAM and registers, that's kind of like, store things kind of semi-permanently. As long as there's electricity, they can store things. DRAM has this problem of forgetting in some sense. They have leakage. So if you just leave a specific cell of DRAM alone for a few seconds, the data will be gone. But that's not the case for registers or for the SRAMs. So what we need to do for DRAMs is what's called a refreshing. So we need to kind of like, go through the same lines over and over again and refresh it. Think about it as kind of like, a glass of water that has a small hole in it, and then it's very, very slowly the water goes down and down and down. So what we need to do is that we occasionally needs to pour some water in it in order to make sure that this DRAM does not lose its state. But on the other hand, it's very, very fast. It's very, very efficient in terms of area. Okay, so when we are talking about your RAM in your computer, when we are talking about, I have an 8 GB RAM, we are talking about this DRAM thing here. Okay, the SRAM and the registers are, your SRAM is basically what's called a cache, which we're going to extensively talk about, and register is basically the register file that we talked about. We only have 32 of these. We usually have only 32 of these. We have a few kilobytes of this. Oops, sorry. And then we have megabytes or gigabytes of DRAM. So that's the range of these different memory technologies. And the reason that we use different each of these is that if we want speed, we have to go here. If we want area, we have to go here. So this is kind of what we call as memory hierarchy. And there's additional memory hierarchy. There is also a disk, which is your hard drive, which is much, much more area efficient than the rest. You can have terabytes of data stored in this with much lower power. But on the other hand, it's very, very slow. We are talking about orders of magnitudes, 2 or 3 order of magnitudes slower than DRAM, and up to 100 order of magnitude slower than registers. Okay. But on the other hand, you can store terabytes of your data. And another thing about the disk is that it's non-volatile, which means that even if it's not connected to a source of energy, it still can retain the information. But all these others, if you turn off your computers, data on your registers, on your SRAM, on your DRAM, all of them will be gone. But the data on your disk will stay forever. So this is like a non-volatile memory, and these are all volatile memory. Okay. So that's the story with different memory technologies. We will so just give you a trend from registers to DRAM to disk. We are moving from smaller and faster to bigger but slower, and from more expensive and more power hungry to cheaper and more power efficient. So that's kind of like the story of starting from a register, which is on the top, all the way to the disk at the bottom. Okay. And in order to utilize all of these together, we use this thing called memory hierarchy. So instead of like saying that, I'm only going to use registers, or I'm only going to use disk, we're going to use what's called a memory hierarchy, which we will spend a good portion of this class on memory hierarchy. We will, about 4 lectures, we will talk about memory hierarchies. Okay, so that would be it for now about memory hierarchy, but we will revisit this and talk about these slides in much more detail. Any questions about memory hierarchy? Okay. So now let's go back to our instruction fetch. Now we understand that how the process of reading things work. So to give you an idea of how does this work, is that this instruction memory needs to be large, so we cannot use it as a register file. We need to use it as an SRAM or a DRAM. We typically use an SRAM for our instruction memory because we need to be fast enough. So when we're talking about instruction memory, we usually talk about an SRAM. And when we are talking about PC, this is a register. Okay. So now another question is that how many bits do we need for the address? Okay, because we know the output is always has to be 32 bits. Why? Because our instructions are 32 bits, so whatever we read has to be 32 bits. But what is the number of bits that we need to send to the memory? In other words, what is the address size? And if you look back at the design that I gave you, I told you that memory is basically this 2D array of W and L. And this L is basically telling you how many lines that you have. The number of bits that you need is basically log 2 of L. And that's basically the number of bits that you need. And it's not something that is always the same. Depending on how much you pay for your computer, your instruction memory could be smaller or could be bigger. So if you use all the, so first of all, the PC itself is 32 bits. So at most we can have 2 to the power of 32 lines in this memory. But 2 to the power of 32 lines is a lot of memory because each one is 1 byte, right? So we are talking about giga of 4 gigabytes of memory for our instruction memory, right? 2 to the 32 is 4 giga. And each line is 1 byte. So we have 4 gigabytes of memory if we use all the 32 bits. And if you remember, I said that SRAM is usually in order of kilobytes. So when we are saying that when we are addressing our instruction memory, we typically don't use the entire bits of our PC. We only use a portion of PC to address our instruction. Which bits we use? We typically use the lower significant bits. So let's say, for example, we want to use 1 kilobytes of memory. We need 10 lines of this. So we use, for example, bit 0 to bit 9 of PC in order to address this memory. Okay? And the rest is basically ignored. Okay, this is just the way that we address our instruction memory. If someday we update and upgrade our instruction memory and our instruction memory now becomes, for example, 64 kilobytes, then we can add 5 more lines. So then we can add maybe bits 10 to 14 to this system as well, and so on and so forth. So how many bits are we using from PC to address the main memory, the instruction memory? It really depends on the size of our instruction memory. Okay, and in order to calculate that, for example, I'll give you the size of the instruction memory. You have to consider that each line is 1 byte, and then calculate the number of bits required to address this entire memory. Does that make sense? Any questions? Say louder. So the question is that is instruction memory a cache? For now, just forget about the term cache. Once we get back to the memory hierarchy, I will talk about it. But for now, assume that your instruction memory is an SRAM, which is typically in order of few kilobytes. Say it again. Can I write SRAM? So the question is, can I write to SRAM? Yeah, of course. So all these memories you can write to. And that's the way the operating system will load the program, because at some point, we need to load the machine code into the instruction memory. So we need to be able to write to it, and we also need to be able to read to it. In this specific scenario, we don't need to write to it. We just read from it, but you can write to it. So the question is, what is the width of our memory? Remember, we said that our memory should be byte addressable. So each line is 8 bits. And then we usually just read 4 of them together. So the output we are always assuming is 32. But that's why if you want to read another instruction, we have to do PC plus 4, not PC plus 1. So the question is why I said we only need 10 bits to address this. I assume that we have. So if I tell you that we have only 1 kilobyte of instruction memory, then the question is how many bits do I need to address the entire memory, the entire instruction memory? And you have to go and see 1 kilobyte is how many bits? Is 2 to the power of 10 times 1 byte. So I said that each line is 1 byte, so this part can be ignored. It means that we have 2 to the power of 10 of these lines, and 2 to the power of these lines, log 2 of that is the amount of bits that we need to address this, which is 10. So we need only 10 bits to address this 1 kilobytes of memory. If I say now we have 64, then it means that we have 2 to the power of 6 times 2 to the power of 10, or 2 to the power of 16. So we need 16 bits of memory, and so on and so forth. If it's bigger, becomes bigger and bigger, you need more bits. Does that make sense? So the question is, where does that 2 to the power of 10 is coming from? So the first thing is that you have to know what is the size of your memory, okay? And what determines that size of memory is that where you're going to go and literally buy a piece of memory. So for example, you're going to pay X amount of dollars to buy 1 kilobyte of memory. So when you're buying your PC, or when you're setting up your PC, you will put some amount of memory there. It could be 1 kilobyte, it could be 10 kilobytes, it could be 1 megabytes, and so on and so forth, right? Once you know that, then basically the hardware needs to decide how many bits do I need to address that memory. Does that make sense? Mm-hmm. So the question is that, so that's what we are saying. So 2 to the power of 10 is 1024, and that's what we, yeah. But we were saying 1 kilobyte is 1024. Mm-hmm. Yes. So the question is, what is the how many bits do we need for addressing the memory? And the answer to that was that depends on the size, the number of lines in our memory. Remember, the width is typically just 1 byte. That doesn't change from one memory to another memory. If you buy another memory, that would be still 1 byte. So the number of lines, which consecutively decide how many bits do you need to address this memory, depends on what is the size of the memory. So your input should be, what is the size of my memory? Once you know that information, then you decide on the number of bits and everything. So in this example, I start with this. I told you that you have 1 kilobytes of memory. Then you have to then calculate how many bits do you need to address that. A little bit louder. So the question is, what do we do with the rest? You just ignore it. And there could be collisions, right? There could be scenarios where, for example, let's say we are only using the first 10 bits. So this address, for example, and this address, if their first 10 bits are the same, is the same for us. So it's, again, the operating system jobs to make sure that these are not the same. And once we get to the addressing of the memory, we will talk about what's called a virtual address, and you will see how we actually handle all these things.
So just to clarify, when we bring out how many bits we need to address,
Mhm.
we just take the instruction set, just straight into bits, so 2 to the 5, and then you multiply that by the size of the memory, which should this is.
No. So the question is that in order to figure out the size of the memory, you take the 32-bit instruction size, and that used to decide what's no. The instruction size has nothing to do with your. Okay.
Just like figuring out the log base to the 10 equals 10, like what you have there. Finding that value, you multiply the size of the memory, which is I don't know 1.5.
Yeah.
The size of the instruction, which in our estimation is 32, right?
Mm-hmm.
And then you multiply those two. And I'm confused there. Like, I think I missed it. You have using 6 times that last value, and then below that you have log base 2. So I'm just confused on that one.
Yeah, so let me do it one more time. So it has nothing to do with our 32 bits. So don't be confused with that 32 bits. So our width in our memory is always 8 bits, always 1 byte. So doesn't nothing to do with that we are using 32-bit instruction set or 64-bit or 8-bit or whatever. We always, for compatibility reasons, we are always assuming that W should be 8. Okay. So don't think otherwise if somebody explicitly say that for some reason we are changing that. So it's always 8-bit or 1 byte, each of these lines. Then the question is, how many lines do we have? Okay, so we have 1 byte each for each line. We have to know what is this total size of our memory. So for example, I gave you this example of 1 kilobyte. So 1 kilobyte is 2 to the power of 10 bytes. Okay, and each line is 1 byte. So we have 2 to the power of 10 lines. Okay, so for addressing 2 to the power 10 lines, how many bits do we need? We need log 2 of that. And in this case, it means 10. So you need 10 bits to address 2 to the power of 10 elements. Each element is 1 byte. Okay. So how many instructions does this include? So for that, then you need to divide it by 4 and say, okay, 2 to the power of 10 lines divided by 4 is our number of instructions that we can store in this memory. Because every instruction is 4 bytes. We have 2 to the 10 power of these lines. Each 4 is 1 instruction, so I divided by 4, and that will be our number of instructions that we can save in this, which is 2 to the power of 8, 256 instructions. Okay. So the question is, does the instruction memory include the data of the program? As I said, these are all part of the same memory, which is much bigger than this. But for now, just assume that instruction memory is physically separated from your data memory. So your instruction memory only includes instructions. Your data memory only includes data. Later on, we're going to combine the two. Okay. So again, remember that we use word. So we read 4 of this together. So the next instruction stores at PC plus 4 and not PC plus 1. PC plus 1. So that's it with the first part. We successfully read instructions or fetch instruction for our instruction memory. Now the question is all these other steps. We need to load the operands, we need to execute them, and so on and so forth. So let's move on. So remember, I told you that there are 3 types of operands we need to load. There's a register file, there is immediates, and there is memory. So let's see how we can load these instructions. So load these operands. Let's start with the simpler one. The simplest one is the immediates. The reason that it's the simplest one is because the immediates is already embedded into the instruction. So remember, when we are reading the instructions from the instruction memory, we're going to get a 32-bit value. And if you go back and look at this table, the immediates is already stored in this 32-bit value. We just need to wire them together in the right format to create that number of bits that we want for the immediates. For example, in this S-type instruction, we need to wire bits 7 to 11 plus this 25 to 35 together in order to create our array, our value. Think about it in C program. What you will need to do is saying that my immediate is a concatenation of im or instruction 31 to 25 concatenated with instruction 11 to 7, for example, something like that, right? But it's complicated because some of the bits are moved, so you need to actually do some bitwise kind of operation in order to make sure that your immediates is correctly wired. Okay, so basically think about it as one instruction as an array of 32 bits. What you need to do in order to extract your immediates is going to and checking the right indexes in your instruction and then just load that into one variable which you call immediate. And that's how you get your immediate. Okay. And then you see for different type of instruction, this wiring has to be different. So we need to first figure out which instruction this is, which I'm going to talk about. And once we know that, then we can wire them correctly. The second is reading the registers. And remember, I told you that we have 32 of these registers, and they are actually all stored in this thing called a register file, which basically nothing but, again, an array of 32 lines, and each line is 32 bits. It's not 1 byte anymore, it's 32 bits, okay? And what we do is that, remember that sometimes we have RS1, sometimes we have RS1 and RS2, and sometimes we have RS1, RS2, and RD. So that's why we have read register number 1, read register number 2, and read register number 1 actually sends the data to read data number 1, and read register number 2 points the data to read data number 2. So our outputs are two of these valid, two 32-bit value, which is RS1 and RS2. And on top of that, we have write register and write data. This write register is basically RD, and this write data is the value that we want to store in RD, which I'm going to talk about later. So again, going back, we have read register number 1, which is RS1, read register number 2, which is RS2. And as you can see, we only need 5 bits to address this. Why do we need 5 bits? Because 2 to the power of 5 is equal to 32. We only have 32 of these registers. So we only need 5 bits for addressing this. And we can address them at the same time. It's not like the memory that you need to address them one by one. Register file has this additional ability that you can read 2 things at the same time. So you put RS1 here, RS2 here. And similar to the way that instruction memory works, you put the address, you get the data after some delay. So this would be the value of RS1. And this will be the value of RS2. Okay? And on top of that, we have these 2 things on the bottom here. So this is basically your RD. Again, it's 5 bits because RD is also a value between 0 to 31. So it only needs 5 bits. So this is your RD. And RD needs data to be written too, right? So these are your outputs, but this is your input, right? And this is a 32-bit value, okay? So register file is a very busy kind of like, block that has all these things together and can handle them all separately, okay? So you can read from register file from RS1, you can read from RS2, and you can write to RD all at the same time. They are completely separate and independent from each other, okay? And inside this is basically some circuitry to handle these requests. And the most importantly, it has all the registers inside this bank, this register file. Okay. So basically, where do we get these RS1 and RS2 and so on? Again, if you go back to the instructions, you see some of the bits in that instruction has that RS1 and RS2 and RS3, sorry, not RD and so on and so forth, right? We just need to, again, get the instruction and wire it correctly to get those bits that we want for RS1, for RS2, for RD, and so on and so forth, okay? So this is for RS1, this is for RS2, and this is for RD, okay? So this is the second operand. And then the third type of operands are memory. Our memory using this thing called data memory, which is different, as I said, separate from our instruction memory. And it's similar to our instruction memory. It takes the address and it gives you the data. One thing that is different from instruction memory and data memory is that you don't want to write things to your instruction memory, but you want to write things to your data memory, right? So you have also the write data if you need to. And this is basically for store instructions, okay? For now, forget about these blue lines here. I'm going to get to those memwrite and memread and all those things later on, okay? And as I said, in order to keep things simple, for now, let's assume that the data memory is a separate structure than the instruction memory. Later on, we're going to combine them together, okay? So data memory, very similar to instruction memory. The additional thing that it has is the write data, because sometimes we want to store things into our data memory as well, okay? Okay, so now that we know kind of like how to get them, the question is that all these instructions, different instructions, have different operands. Some of them has RS1 and RS2. Some of them has RS1 and immediate. Some of them don't have any operands. They only have memory. So how do we know that which of these instructions should we read? Like, how do we know that this is an R-type instruction, so we need to use RS1 and RS2? Okay, so that's the main question. And even bigger question is that how do we know that what type of instruction this is? Because very first thing that we need to know is that whether this is an R type, an I type, and the hardware itself is not intelligence to know these things. We need to add some functionality to our hardware in order to understand the difference between these instructions, okay? So in order to find that, we need what's called a controller, okay? So the controller is the one that is basically read the instructions, read that 32-bit value, and give us all these answers that we want to, that whether this is an instruction, this is an add or an subtract, how many of these bits do we need to read, whether we need to write to the memory, whether we need to read from the memory, and all those things. So all of that happens in this thing called a controller, which is, again, a separate logic that we need to implement in our system, okay? So when we are thinking about the whole thing, basically every CPU has two major components, the data path and the controller. The data path is the part that just functional units, the instruction memory, the PC, wiring, register file, all these wires and these elements that we just connect to each other, that is called our data path. And the controller is the one that's basically tell each of these different components what to do, whether you have to read or whether you have to write, how many bits do you need to read, and all those things. So think about the controller as kind of like, someone that controls a big orchestrate and tells each person what to do. Okay? So let's have a quick break here, and then we come back and then talk about the designing of the controller. So our von Neumann model would be the CPU and the memory, and they work hand in hand. And this basically becomes our computer. And the computer itself also interacts with some inputs and some outputs, obviously. And what I just said was the CPU itself consists of two parts, the data path and the controller. Okay, so our regular design of CPUs is designing the data path and designing the controller together creates of our CPU. Okay. So now let's actually go and check out what is the role of controller, how do we design a controller, and all those things. You notice that when I was showing the entire system and then these different individual blocks, there were these blue lines that goes inside each of these blocks. And I told you to ignore those. And as you can see, each of them has a name like a memread or memwrite or readwrite. These are actually the signals that is coming from the controller. So think about the controller as this block that's kind of sit on top of everything and has, inputs to every single block that we want to use in our data path. And in order to distinguish between our wires and our inputs and outputs in our data path versus our inputs and outputs from the controller, we typically show them in blue to make it this different. So whenever you see in our slides and our figures that something is shown in blue, it means that it's coming from the controller. Okay, so we're going to get into these control signals. For example, for data memory, we have two very important control signals, the data write and data read, or memread or memwrite. So let's actually go into what are these, how do we create them, and what is the role of each one. Any questions so far? Okay. So as I said, the controller, think about it as it sits basically between our instruction memory and our register file. The input to the controller is the instruction, okay? Because in order to understand what we need to do with that instruction, we have to read the instruction. And we typically read the entire instructions, and that would be the input or controller. And that's the only input that the controller really needs. And the controller creates a bunch of outputs, which we're going to get to what are these outputs. And that would be based off this logic that's happening inside this controller based off the instructions, okay? So inside the controller, let's think about what are the steps that the controller. So when we are designing the controller, what exactly do we need to design? So let's first write a step-by-step algorithm for the controller, and based off that, implement that in hardware. So the first thing is we need to fetch and read the instruction. So as I said, that's the part that's done with PC and instruction memory. And that goes directly inside our controller. So the controller now has the instructions, all the 32 bits of the instruction as its input. So this part is done. Then the second thing is what we call decoding the instruction. Remember we said that we have various different, instructions. We have like add and add-I, we have load, stores, we have different types of stores, we have different types of loads and all those things. So by decoding, it means that we need to understand which instruction this is, okay? And basically kind of read this different operands within that instruction, yeah. So the question is ALU part of the controller? No. ALU is part of the data path. The controller is just to understand what this instruction is, okay? So once we do the decoding, then of course we need to execute this instruction. And for executing, we need to know what is the operand, right? So another role of the controller is basically detecting what type of instruction this is. Is it an R type? If it's an R type, whether it's an add, whether it's a sub, whether it's an XOR, an AND, and all those things, right? So for executing, the controller also needs to figure out what is this operation that needs to be done, and based off that, issue a control signal. Finally, for saving the results, as I told you, again, we have two options. We either save the results into our register file or save the results into our main memory. And the controller needs to, again, figure out whether this is the storage to the register file or whether this is a storage to our main memory. And finally, there is a PC part that I didn't show here, but there is a PC part as well that I'm going to get to. Okay, so now that we know that what controller needs to do, basically the controller needs to get the instruction and make all these decisions, whether how many operands do I need to read, whether this is an R type or I type, what type of R type, whether I need to store this into register file or main memory, what should I do with the PC, and so on. How do we build such a step-by-step system in hardware? And I think you probably know the answer. Any suggestion of what we need to basically implement? What is the equivalent of this in hardware, if you remember your M51 course? Anybody? So we need, anybody? So we need a finite state machine, an FSM, right? So basically what this is that all of them starts from an init state. And then we're going to say, oh, this is an add, this is a sub, and so on and so forth. So we're going to have a bunch of these different states, and in each of them, we need to make some decisions. So this is actually the definition of the finite state machines, or FSMs. So for those of you who have no idea what FSM is just a mathematical model of the computation. Basically, what we say about the computation is that we map it to a bunch of states. And we said that all of them start from one state, which we usually call it the initial state. And depending on some of the inputs, for example, in this case, depending on the opcode, depending on func3 and func7 and all those things, we make a decision whether we have to check, this is an instruction add or this is a subtract. So we go to that specific state, and within that state, there could be multiple other states, okay? And the main thing about the finite state machine is that for every single inputs, at any given time, you only add one specific state. You cannot be in two separate states. So for every instructions, you only add one specific state, and you can move on to the next state and next state depending on the inputs. But for a given time, for one snapshot of the time, you're only at one state. And the word finite means that the number of states are not unlimited or not infinite, right? So there's only a few states for each. So for example, if you have 50 different instructions from your init stage, you can go to any of these 50, and probably from those 50, you can go to another set of instructions and so on. So there's a finite, it could be so many, but it's a finite number of states, okay? And then each state has some condition to transition to another state. So we usually need to show how do we transition from one state to another state. And with that, we can actually progress through our finite state machine. And for instructions in this specific case, in our example, all of them start with the init state. Depending on the instruction, we move to another state and another state. We do all those steps that I told you, reading the operands, executing, storing, updating PC. And once we are done with the updating PC, we have to go back to our initial state and continue the story again and again and again. Okay, so this is kind of like, a repetitive process that we start from one state, we go to another, we go to another, and at some point we go back to our initial state. Okay, so how many states do we need? What are those states? That's what the thing that we need to figure out for our controller in our processor. Okay. So to give you some form of diagram, when we're talking about state machine, we usually like plot something like this, that this state is like our initial state. Usually we start from the initial state. And then if some condition, whatever that condition is true, maybe we transition to the second state. If that condition is not true, we stay at that state and wait for that condition to become true. For example, if it's a branch and we want to update the PC, if these two are like, if RS1 is equal to RS2, that means that we can transition to another state and so on, right? So there's usually one condition involved that based on that, we jump to another state. And we can have a multiple of these states. In this specific example, I'm showing you the 3 different states, but it could be more than 3 or less than 3 and so on, right? So each of them have some condition to go to another state, and they usually also have a condition to stay within their states, okay? So going back to our controller, I told you that we need a finite state machine. And for the processor, think about the finite state machine, a very big finite state machine with many different states, because essentially for every single instructions, we need multiple of these states, right? And I told you, for example, for RISC-V 32 bits, the base version, we have somewhere around 50 instructions. So we at least need 50 different states for this FSM machine, okay? So it's a relatively big finite state machine. If you go back to the design of the life cycle of the instructions, in order to map those states to our FSM, we need to go that step by step, read that step by step life cycle. So all of them start with this thing called the initial state, which is basically just reading the instruction and decoding them. All of them, the very first step in every single state that we have is that they all start from this initial state, the S1, or we want to call it init, or whatever you want to call it. And that's where we need to read the instruction. Then, depending on what this instruction is, we're going to transition to another state, whether you want to call it S2, S3, or whatever you want to call it. There are many of these because there are many different instructions. Some of them may go to the same state, some of them may go to the different state, and so on. So depending on what instruction this is, we jump to that specific state. And then again, depending on whether this is an arithmetic and load or store and so on, from that state, we jump to another state, and so on and so forth, until we reach to the end of that instruction, and then we have to jump back to our initial state. Okay, so this is kind of like, what we should design in our controller. Okay. And then again, as I said, it's going to be repeated. It's going to go back to initial and repeat for the next instructions. Okay. So now that we know that, let's actually get more specific and talk about a subset of instructions. And let's see what are the states, what are the control signals that we need, and how do we transition from one state to another state. In order to make that specific example, I only picked a subset of 10 instructions that we go over so far. So I'm going to only pick add, subtract, and or load word, store word, branch equal. And I'm also going to add add-I, and-I, and or-I. So the total of 10 instructions, 32 bits. I picked this 10 because to make it simpler, we don't want to like add all these 50 different instructions in our finite state machine, our data path, because that makes things much more complicated and very time consuming. But once you learn the procedure and the logics behind the decision that we make, then you can easily apply it to any other instruction. So for example, in your quiz or in your homework, you might see that we ask you to add this instruction or that instruction in the controller. What are the control signals for those instructions? Once you learn the basics, then it's very easy to assign the correct values for all these other instructions. Okay? Any questions so far about FSMs? All right. So to just again remind you about the instructions that we're going to look at, I'm just grab them and put them all together. So we have 4 R-type instructions, 3 I-type instructions, 1 load and 1 store, and 1 B-type instruction, the B branch equal. Okay, and the things that you need to pay attention to in order to distinguish these instructions from each other, which the first role of the controller is first understand which instruction this is, we need to rely on 3 things. We need to rely on the opcode, the func3, and func7. So as you can see, all of them has this first 7 bits as their opcodes. And if you pay more attention, you will see that all the R-types instruction actually use the exact same opcode. So by looking at the opcode, the controller will understand that whether this is an R-type, whether this is an I-type, or whether this is a load, or whether this is a store or a branch. So basically, at the first step of the controller, what the controller will see and understand is distinguishing between 5 different categories by just looking at the opcode. What the controller does is basically think about this as a big switch case. In hardware, this will be implemented as a lookup table or LUT, which all it does is that it's going to read this 7 bits, and based on that goes either into the R state, the I state, the load word state, the store word state, or to the branch state. Okay? So from our initial state, the first thing that we're going to branch out is that I'm going to read the opcode, and then we're going to jump into this different state. Okay? That's the first thing we do. Now we have the problem of, okay, all these 4 R-type instructions or all these 3 I-type instructions are exactly have this exactly same opcode. So how do we distinguish between the 2? Then that's where we're going to use this func3 and func7. And the reason that we need both of these is that I'm only showing 4 here, but in reality, the number of R-type instructions is actually more than 4. So we need to have multiple bits in order to distinguish between them. One thing that you might think is that why didn't we use different opcodes for each of these instructions? It's just to make things more efficient in terms of size. Because remember, only R-type instructions needs func3 and func7. The others can use this space for other things. So for example, the I-type instructions can use it for bigger immediates. So we kind of, instead of like having a bigger opcode in order to handle everything and potentially waste that space for these other instructions that doesn't require that, what we do is that we say that, okay, I'm going to do this categorization in 2 steps rather than 1 steps. And this way I can reuse this space and this space for other instructions, for other things in other instructions. Okay. So for R-type instructions, which we have a wide variety of R-type instructions, we need to rely on both func3 and func7. But for immediate instructions, we, for example, only rely on func3 because there is only a handful of instructions that are different in immediate. And for load and store and for branch, we don't care, right? Actually, for branch, we do care because there is like branch equal, branch less than, and all those things. So you will see that there's actually another func3 for branches, which in this case, since we only have 1 branch instruction, we don't care about the func3. But if you have multiple of those, then we have to take a look at this func3 as well. Okay, is that clear why we are using func3 and func7 and opcode? Any question here? Awesome. So our controller is basically, so then start with this, and then for R-type instruction, it has to check the func3 and then decide whether it's an add or sub or whatever, or in some cases, it also has to check both func3 and func7 in order to make that decision, okay? For immediate, we only need to check func3. For load, we don't need to make any checks. And for branch, we also need to check func3, okay? So the decoding part of the R-type instruction is slightly more complex, require more work because we need to go deeper into our instruction in order to figure out whether this is an add or whether this is a sub. But the reason for that is that we save that for all the other instructions in our ISA. Okay. The second thing that the controller needs to know is that, okay, now I know that this is an R-type. Now I know that, for example, this is an add. What I need to do next is I need to read the operands, right? So for R-type add, I need to read RS1 and RS2. But for add-I, I need to read RS1 and immediate. For load, I need to read RS1 and immediate. But for store, I need to read RS1 and RS2. And the immediate is also this funky type of, immediate that some of it is in this side and some of it in this side. So I need to kind of like wire them together somehow. So the controller's job is kind of issue, once it knows that how many of these RS1 or like what type of operands we need to read, it needs to issue some control signals to our register file and to our memory, telling them that, oh, this is the instruction that needs both of these RS1 and RS2. This is an instruction that only needs RS1. So we need to issue some control signals, some of those blue wires that I show you, to these other elements in our data path, and tell them that, oh, we need these things. Okay. So that is with RS1, RS2, and RD. And then, of course, as I said, the immediate one also has to be properly wired. So sometimes we need to sign extend them. Sometimes we need to sign extend them bigger or shorter and all those things. Okay. So this is kind of like, if you go back to our data path, you will see that we have these blue signals in our system. And these blue signals are exactly those things that I told you. So let's actually go through them one by one. So so far, we have our PC, we have our instruction memory, and we have our 32-bit instructions, okay? Then I told you that there is a register file that needs to be connected to this. I'll get to that point later. But let's actually talk about the next PC first, this portion of the data path. So this is our PC, and our next PC should be either PC plus 4, or it should be jumping to somewhere else in our memory, right? So let's just start with the simple task and creating just PC plus 4. So all we need to do is that add this additional wire here and add this additional adder, which is simply takes this value here, this 32-bit value here, and this constant, this value equal to 4, and add them together. And then we just put this back into the PC. And remember, this is a clocked register. So the next time that the clock comes in, the PC will be updated. And now we're assuming that every instruction takes only one cycle. So in one cycle, we finish all the instruction. In the next cycle, we're going to read and execute the next instruction and so on. So what we are building here is we're basically saying that whatever the value of PC is here, we're going to add it by 4, and we're going to send it as the input back to the PC. The next clock comes in, and then the PC, the new PC or the next PC will be equal to PC plus 4. Okay? So this is how we create our next PC. And for now, let's just assume that the only next PC that we can get is PC plus 4. For now, forget about the jump and jalr and jal and branch equal. Let's assume that we always get PC plus 4. And that's how we create PC plus 4. Any questions here? Is that clear why we're doing this?
Or they represented like going from the archetype to like a specific operation as separate states.
So the question is that for controller, I told you that from R type, we go, depending on func3 and func7, we go to another states, and this is what we're going to actually implement or not. Let me answer that question when I'm talking about the ALU, and you will see how do we implement that in real hardware. The short answer is no. For all of them, in terms of FSM, they are the same. But conceptually to understand it, let's think about it that we first understand whether this is an R type or I type. Then within the R type, we need to make a decision whether this is an add or subtract or XOR or whatever. Okay? Any other questions? Okay. So we build our next PC. And I told you again, going back to the register file, I told you that register file itself is this fairly complex structure of having 2 inputs for register 1 and register 2 for data, for the RD and so on. So now if we connect these two, you will see that, basically what happens is the output of your register basically needs to go to the next part of our data path, which is the ALU, the arithmetic operation unit. What the ALU does is basically either doing sub or add or XOR or subtract and all those things. We will get into what are those operations, but if you connect these things together, all of them together, you will get to this point here where we have our register file, we have our ALU, and we have our data memory. And if we have a bunch of these multiplexers, these blue signals here, and there is this connection from the output of the memory to this register and all those things. So now we need to actually go through these and kind of break it down why we are adding this multiplexer, how do we connect these wires together, and what are these blue signals here, okay? So I'm going to describe this one by one for you. So the first thing to pay attention to is that your instruction actually goes into your RD1, RS1, RS2, RD. This is your data register, the data for your RD, and this is the value of your RS1, and this is the value of RS2. Okay. And this is basically, if you go way back, you will see that basically in order to understand which wire needs to be connected to where, this is our basically our map. We're gonna look at these bits and these bits, and we're gonna connect these instructions to our register file. So this is basically the reason that I'm showing it this way. Is this is going to be the same number of instructions. For example, instruction bits 11 to bit 14, or bit 14 to bit 16, or so on and so forth. So this instruction, which this itself is 32 bits, is divided into smaller bits. So this is a 5-bit number. This is a 5-bit number. This is also a 5-bit number. So this goes into our register file. Another thing that happens is that the entire 32 bits goes into the immediate generator, because remember I told you that our immediates are 12 bits or 20 bits or 16 bits, depending on what instruction do we have. And what we need to do is that we need to make them all 32 bits. So what happens is that our immediate generator is basically sign extend that for us. So this is the part that we get variable size for immediate, again, coming from the instructions. And here we do all the wirings. If you remember, some of the instructions has 0 to 4 here, and then they had 5 to 11 somewhere else. So this immediate generator is basically this block that take care of this for us. And the output of this would be a 32-bit value that comes from here, okay? So to kind of navigate through this, so far, we have the 32-bit instruction. We divide it into 5, 5, 5, and goes into our register file here. In order to know which of those 5 bits needs to go to RS1 and RS2, we have to go back and look at our table. And then in addition, we have the immediates here, the 32-bit here, all the instruction. It goes to this immediate generator, and it will do the wiring for us depending on the instruction. And at this point here, I have the 32-bit value of immediate. So this is my immediate, okay? Sign extended, 32 bits, perfect. And this is the output of RS1, and this is the output of RS2, okay? So far we know what's going on this left side of this figure. Any questions so far? So the question is that, does the immediate generator use a controlled signal? Is that, yes, it does. We didn't show it here. Once we actually get into the immediate generator, the logic inside it, we will talk about how do we create that. But for now, assume that the immediate generator knows what this instruction is, and based off that, do the wiring for us and do the sign extension for us. Does that make sense? Any other questions? The right data comes from here, which we haven't get to. So for now, wait for the right data, because storing the results, if you remember, was step number 4, which was kind of like toward the end. For now, we're just fetching the operands from our register file and from our immediate. So at this point here, we have our immediate as the way we want to. We have our RS1 the way we want to, and we have our RS1 and RS2 the way we want to. Okay? Okay, so we have our 32-bit value here. Now the question is, what is this mux and why do we need that? So if you look at this part here, the input of our ALU, which is this unit that does the arithmetic operations for us, it needs 2 inputs, right? The first input is always RS1. The second input of the ALU is connected to this multiplexer, which says that either the input to the ALU would be RS2 or it would be our immediate. So the ALU has 2 inputs. The first input is RS1. The second input is either RS2 or our immediate. And why do we have such a scenario? If you look back at our 10 instructions, all of our operations was either done with RS1 and RS2 as the operands, or was done with RS1 and the immediate as the operand. Okay? And how do we distinguish between these two? There's this control signal called ALU source. It's just 1 bit that comes from the controller, and the controller will say whether this has to be coming from the immediate or whether it has to be coming from the RS2. How does the controller know that? Remember, we talked about the states. We said R state and I state. So the controller will read the instruction, will read the opcode. If it's an R-type instruction, it will say that the ALU source should be equal to 0. If it's an I-type instruction, it says that ALU source should be equal to 1. You can also check what for load word, for store word, for branch, what should be the value of the ALU source. So generally, if we need RS1 and RS2 for our operation, ALU source has to be equal to 0. And if we need the immediate with RS1, then ALU source has to be equal to 1. Okay? So adding these together, we now reach to this point here. which we know what is the inputs, the two inputs of our ALU. Okay, right? The next thing is that now we have the inputs to our ALU. What should we do then? We have this control signal, which is 4 bits. It's 4 bits because we have at most have 16 different operations. I'm going to get to later, but this ALU operation control signal is basically tell this ALU what operation to do. So think about it this way. If it's 0, 0, it's an add. If it's 0, 1, it's sub. If 1, 0, it's maybe XOR, and so on and so forth. I'm just making this number up, so it's not an actual numbers. But again, this is what is coming from the controller, and the controller will tell the ALU what to do with each instruction. Again, in our FSM, we start with the R type, and then we go to func3, and in func3, we basically create this, okay? So we have this point here, and that's where I'm going to stop. And then I'm going to add the other things later step by step. But you get the idea, right? So depending on the instruction, the controller knows what to do, issue these signals. We have adding mux here and there to actually create what we want from our processor.